Hello, everybody, and welcome to the 5th Joint Institute of Physics, or IOP, and German Physical Society, DPG, panel event. My name's Tara Shears, and I'm the Vice President for Science and Innovation at the Institute of Physics. Now, this series was established in 2020, when the IOP celebrated its 100th anniversary alongside the DPG, who were celebrating their 175th anniversary. The first event focused on climate change, and it started a fruitful tradition and collaboration on the series between our organisations. We're really proud of international relationships like this. All of our scientific communities recognise the vital importance of international collaboration to deliver the best results. Strong, long-term, international collaboration, it must be maintained if we're going to remain in the vanguard of scientific discovery and innovation and realise the knowledge-sharing, economic and political benefits of science diplomacy. Our organisations recognise the importance and the value of representing perspectives from both the UK and Germany, and in bringing those points of view together. And in this way, we discuss current global challenges and the role that physics plays in helping to solve them, whilst highlighting the benefits of a multidisciplinary approach to tackle these challenges for the benefit of society. We hope that our collaboration will continue to serve the interests of the physics community, and we would be delighted to hear from you all about what topics you would like to see us cover at the next event in 2025. Now, our discussion today concerns the energy mix required for a carbon-free future. And I'm sure you'll agree that physics is essential in advancing the technologies to achieve this. Physics plays a crucial role in scaling up a sustainable energy system and in understanding how different energy sources can work together effectively, all of which are vital if we're going to achieve our goal of a net zero future. At the Institute of Physics, we work with the physics community in academia and business to shape science, technology and innovation strategies in order to drive societal and economic impact, and really, in short, to show how physics can make a better world for us all. And one way we do this is by means of our impact projects. These are community-led exercises that combine expert ideas and expertise from our community with data and stakeholder insights to understand an area, to make recommendations, and then to facilitate actions to strengthen its impact. So, for example, our impact projects in quantum technologies and semiconductors influence national strategies in the UK and some £3.5 billion of government funding. Now, I mention our impact projects because last year's project focused on physics powering the green economy. It highlighted the really central role that physics has in enabling the technologies we need to reach net zero, and the advances that we also need to make to enable nuclear, renewables, energy storage, hydrogen and clean fuels, and negative carbon technologies. It's really relevant to today's discussion and demonstrates how important we think this area is. You can read our report, it's on our website, and if you do so, it shows that physics innovation and physicists are vital to scaling up a sustainable and global green economy and to making a sustainable and just energy transition. Our report called for a range of investment strategies for physics R&D, for business innovation, for infrastructure and for skills in order to achieve this and make it happen. We realise there's no single solution that can achieve this. And these strategies need to be part of a long-term systems approach to leadership, coordination and delivery of the energy transition, one that can drive progress in every area whilst keeping sight of the whole. This area is so important to our lives that we haven't finished our work yet, and a second phase of this work is underway. And working with IOP fellows and community experts, we will carry out technology assessments on high potential, short-term technology advances in energy production, in energy storage, energy transmission, modular reactors and reactor physics, and solar technology. And we aim to publish our findings in March next year, so do look out for them if you're interested. Now, let me turn back to today's event and discussion. I'd like to introduce Karin Zach, the Executive for International Activities at the DPG. Over to you, Karen.
Okay, hello everybody. My name is Karin Zach, coming from the German Physical Society. I'm the elected board member responsible for international activities, and I want to say a warm welcome from the German side to all the participants. I see here more than 120 people. It shows us that the theme we choose is an interesting one, where a lot of questions will arise, and I hope for a lively and interesting discussion. One technical remark. First, we will have some presentations by our panelists, and afterwards, it is possible to ask question. Please, for this, use the Q&A button. Georg and me, we will try a little bit to sort out if very much comes in, a little bit to help our moderator to structure the discussion. But now I want to give the floor to our moderator, Robert Wolf.
Yeah, so welcome everyone to this meeting. My name is Robert Wolf. I'm a physicist by training, director at the Max Planck Institute for Plasma Physics in Germany, in fact, in the northeast, in Greifswald, close to the Baltic Sea. First of all, I would like to welcome very much the speakers here who volunteered, and we have a very interesting mix to talk about future energy. Yeah, so we have colleagues from the UK who will represent fusion, and we will have a presentation about wind energy and basic physics questions, and we will basically wrap up with a more or less general view on energy development, energy mix of the future, which is in fact the topic of this session. The speakers will introduce themselves, so I will not do that now. Yeah, when they start their presentations. As I said, we will start with fusion with Melanie Windridge, then go to Tim Bestwick, Claudia Brunner, and to Thomas Hamacher. And yeah, maybe I forgot one thing to say. So I'm here not in my, let's say, capacity as also a fusion scientist, but I'm member of the energy working group of the German Physical Society. So this is my role today, and I will lead you through the discussion. Yeah, with that, I think we come to 4 presentations, and first one to start is Melanie, please. Go ahead.
Thank you, Robert, and hello, everyone. I'm Melanie Windridge. I'm just going to share my screen for you. There we go. Hopefully, is that okay, Robert? Great. So yes, hello, everybody. It's a pleasure for me to be here. Just a quick introduction about myself. I am a physicist by background. I have a PhD in plasma physics and fusion energy from Imperial College London. And now I work, what I would say, more on the information provision in the fusion industry. I'm the founder and CEO of a company called Fusion Energy Insights, and that aims to keep people up to date with developments in the growing fusion industry, because things are moving quite fast now. We produce a newsletter called the Fusion Energy Insider, which is free, and you can sign up to that if you're interested in being kept up to date. I'm also the co-founder of 2 other companies in fusion. One of them is called FusionX Invest, and that aims to bring together investors and private fusion companies, and we run conferences and provide data. And the other company is called Fusion Advisory Services, and this is more specific deep dive information. So we do things like reports on technical due diligence or market studies or landscape, that kind of thing. So yeah, a lot of information provision in the fusion industry now. I'm interested in taking fusion from the lab and into the commercial space. And so I'm going to give a brief introduction to fusion energy. So fusion is a sustainable energy solution. It's still experimental. It's still something that we're working on. It's actually the reaction that happens in the sun and the stars. So scientists have been dreaming about harnessing this reaction as a clean energy source on Earth from when they first realized, Arthur Eddington and colleagues first realized what was causing the sun to shine. And the reason it would be a great energy source is that it produces no CO2 emissions. It has an abundant fuel supply. It's a safe, controlled process. There's no long-lived radioactive waste produced, and it produces a lot of energy. So fusion is very energy dense. Just 1 kilogram of fusion fuel produces as much energy as 10 million kilograms of fossil fuel. So that's like, 1 kilogram, like a water bottle like this, or a bit bigger actually. That's half a kilogram. But anyway, like that kind of weight is as much as hundreds of truckloads of coal, all with 0 CO2 emissions. And Phil LaRochelle, who's an investor at Breakthrough Energy Ventures, he says, we have no idea what's going to be made possible by being able to use fusion power. It's like the discovery of fire. He says it's like entering into a new energy paradigm. It's like a new industrial revolution. So it has huge opportunity, but it is very challenging to make little stars on Earth. So fusion is a nuclear reaction. It's actually the opposite of nuclear fission, which we use for nuclear power at the moment. Fission is the splitting apart of a larger atom into smaller ones, and fusion is the joining together of the smallest, lightest elements, nuclei, into a larger one. And both of these processes release energy. So on Earth, the particles that we'd be using, the nuclei that we would be using primarily are deuterium and tritium. There are other fuels that can be used, but deuterium and tritium is the easiest reaction to do. And these are both isotopes of hydrogen, or heavy hydrogen. And so the deuterium and the tritium would just come together. They need to be moving very fast because they repel each other. The protons and neutrons rearrange themselves, and out of the reaction, you'd get helium and a neutron. And so the helium is the waste product, so it's a safe waste product. It produces a neutron, which has a lot of energy, and we want to harness that energy and use it to make electricity or just heat. But it is a very fast-moving neutron, and so it can be problematic for the device itself, for the walls of the machine. One of the challenges. So in terms of the safety profile of fusion is not fission. It's very different. Fusion is very, very hard to do, which makes it inherently safe. There's no risk of meltdown because it's just very, very difficult to get the reaction to happen in the first place. So if the conditions aren't right, the reaction just stops. There's also less radioactive material, although the radioactivity and the waste does depend on the design choices. So those are things that are still being determined as people are designing power plants. Studies that have been done have shown that even extreme hypothetical fusion accidents would not have significant impact to the public and would not require evacuation. And so because of that, governments in the UK and the USA and others are planning to regulate fusion differently to fission. And those are discussions that are ongoing at the moment. So I said that fusion is the reaction that powers the sun and the stars. And so in order to do it, you have to get the conditions that we find inside of stars. And this is why it's such a challenge. And 3 of the main parameters that we use to measure this, or to measure progress, is the density, the temperature, and the energy confinement time. And that energy confinement time is simply like the time it would take for like all the heat or the energy to leak out of the plasma or the fusion fuel if you were heating it. And so we talk about plasmas because when you the temperatures that you need for fusion are in the hundreds of millions of degrees. As I said, we're trying to make little stars, so you have to get your fuel very, very hot, and that means that it's in a plasma state. So 4th state of matter, you have solids, liquids, gases, and then you have plasma. If you give your gas enough energy, you're actually going to strip the electrons away from the nucleus of the atom, and so you get these separate charges moving around in your gas. So you have an electrically charged gas, which is a plasma. So that's what we're always talking about when we're talking about about fusion, and fusion is all about confinement. It's how do you trap or confine that plasma. You need to get your fuel dense enough and hot enough for long enough for fusion reactions to occur. So that's what those three parameters are there, getting them close enough together, hot enough, so moving around fast enough that they can slam into each other and fuse, and keeping those conditions long enough for the fusion reactions to get started and then hopefully heat up the fuel themselves. Now, within these parameters, there is some wiggle room. So fusion temperatures generally hundreds of millions of degrees, but you could say have a higher density and a lower energy confinement time, or a lower density and hold it for longer. So there is a bit of wiggle room in these conditions, and that's led to lots of different approaches being tried. So different designs, crazy names like tokamaks and stellarators and reverse field configurations, and inertial fusion or laser fusion. So these are all different ways that people are working to try to trap the fusion fuel. The most advanced approaches that have been researched the longest are the tokamak and laser fusion. So historically, fusion was done academically in academic research in the public labs in the universities. And because of the way it was funded, this led to a narrowing, if you like, of the research strands. So that's why it led into the two pathways of tokamaks and laser fusion. And it's resulted in some very big, impressive facilities, such as ITER, which is a tokamak being built at the moment in the south of France. This is very big. If you were to step into that room or into that coil even, it's like looking into a big cathedral. It's a very large machine. And on the laser fusion side, there's the National Ignition Facility, or NIF, equally big facility. These have been making progress. ITER not yet, because it's still under construction, but other tokamaks like JET in the UK have been making very good progress over the years. And the National Ignition Facility a couple of years ago reached a big breakthrough, which is that it produced more energy from the fusion reactions than the energy that was absorbed by the fuel pellet to drive those reactions. And so that was a really important milestone on the way to commercial fusion. It sort of proves that the science is possible. It was the science proof, if you like. So the laser is still very inefficient. So it's not like getting more energy out past the break even of a power station, but in terms of the science and in terms of the plasma physics, it's an important scientific milestone. But now fusion is no longer experimental science. It's actually moving out of the lab, and it's getting a lot of private fusion investments. So since about 2016, there has been a big uptick in the number of private fusion companies that are working on fusion. And at FusionX Invest, we estimate that there's more than $9 billion of private investment has now gone into fusion companies. This is actually a graph from Fusion Energy Base, which shows the increasing increasing private investment into fusion over the years. And so this is getting quite significant now. So a quick rundown on some of the progress in recent years. This is something that we follow as well in Fusion Energy Insights. If you want to look at our blog, we put a lot of articles out about the news and what's been happening and trying to comment on the significance of the news. And we've been seeing things in recent years like public labs breaking fusion records, private companies are validating their approaches, they're developing technology, they're forming industrial partnerships as well, which is significant. There are also governments taking notice. They're setting up fusion strategies, regulatory frameworks, and there's a lot of talk about public-private partnerships and how both sectors work together to commercialize the technology, because fusion now is moving into the engineering phase. It's moving out of the science labs, and people are thinking about how you actually build a commercial fusion power plant. And there are still lots of gaps, lots of challenges. There are technology gaps, there are facility gaps, so facilities that we need to actually develop the technologies. There are whole supply chains that need to grow up, and workforce issues as well. So yeah, there's a lot of challenges, but it is moving into an exciting phase. So thank you very much.
Yeah, thank you very much for this introduction into fusion and the private activities. Maybe I was asked, to write this in the chat. There is a little bit confusion in the discussion about the Q&A question. So as far as I understand, for this session, The chat function does not work for the audience, but please use your Q&A button. That should work for everyone, yeah? So the standard chat function is disabled. Okay, now we come to the next speaker, still on the fusion topic. So Tim, please go ahead.
Hello, everybody. I'm Tim Bestwick. I'm Chief Development Officer at the United Kingdom Atomic Energy Authority. It sounds as if that means we ought to do all things atomic, but we are just focused on fusion and have been for the last few decades. And I'm now going to share my slides. Has that come up okay? So UKAEA has about 2,500 people focused on trying to develop fusion energy as a practical energy source. We've been at this for quite a while, and one of the reasons we have the size and experience we have is that UKAEA was the home to the JET experiment, the Joint European Torus, which ran its first plasma in 1983 and was turned off from its experimental work in December last year after 40 years of operating at the very forefront of fusion and fusion physics. So it's been a real privilege to work with that facility. And we're now taking that legacy and trying to move on to delivering fusion as a practical energy source. I'm enormously excited and positive about fusion, but I'm going to try and temper that with a sort of clear-eyed view of some of the real challenges that we have left to address. And I'm going to start with a recap following on from where Melanie very helpfully left off. I can change the slides.
You have to click the screen.
Yeah, has it changed? So, as Melanie pointed out, fusion has enormous promise to be a low-carbon energy source, an abundant low-carbon source of energy that would really be transformative if we could deliver it at scale. But it turns out to be enormously difficult to deliver. And that's not because there is one particular technical challenge. Actually, there are a whole host of technical challenges. So it is still an early stage technology. It's enormously complex. And it really does appear, however we deliver fusion to the market, that it's going to be a capitally intensive energy technology. But, important but, it's going to be one that could be transformative and could represent enormous economic opportunity. So it's in this transition phase from research topic to commercial implementation. And we don't really know the timing of that, but we do think that actually revenue generation from fusion is still some way off. My personal view would be a couple of decades off, but of course these things vary. And when we talk about the timing of fusion, as we do a lot, it's very important to be clear about what we mean by when will fusion happen. Does that mean when we'll deliver a prototype power plant? Does it mean when we'll have net power energy output? Does it mean when we'll make a material difference to global energy supply? Because all of those are really quite different dates. As Melanie pointed out, there is currently also no clear consensus over the technical approach to achieving the fusion conditions that she described. That triple product where we need to bring the nuclei into sufficient close proximity with enough energy for enough time duration to enable the fusion conditions to occur can be achieved a number of ways. And currently there are some more developed than others. And the heritage at the site I am now at Culham is magnetic confined fusion is the tokamak approach, but the other approaches are available. And until the field matures further, I think we won't see a very clear consensus approved and emerge. And of course, it's quite possible that there will be more than one approach to fusion that will turn out to be viable, perhaps aimed at different parts of the energy market. And fusion involves a whole bunch of technologies that currently are at a very low technology readiness level. So in order to deliver a power plant, there's a lot of technology maturity that needs to be delivered. So what's happening at the moment? Well, the forces of change, as I see them, are first of all that the need for an energy source of the characteristics of fusion become ever more compelling. And we used to start, not many years ago, talks with the need to decarbonise the energy system. We no longer do that bit because the education of everybody about the importance of decarbonisation and the challenges we see in energy supply are now so widely understood. There have been a whole series of really high-profile technical results. Melanie described the experiments at the National Ignition Facility, where for a fusion experiment, more energy was achieved from a deuterium-tritium fusion capsule than was put in the radiation energy that was imploding that capsule. That was a real milestone event, but it is just a step on a long technical journey. So these things might be perceived as a tipping point, but they're certainly not the end of the story of development. Fusion, I think, as Tara spoke at the beginning, is absolutely a subject that needs international collaboration. And the JET experiment here at Culham was a magnificent exercise in European collaboration that is widely admired by everybody who worked on it and around it. And we will need, undoubtedly, to collaborate on an international scale. And alongside that, many countries are now developing quite substantial national fusion programs, which really comes about from this driver about the need to develop this kind of technology in a hurry. The leading fusion companies, an emergent body in the last decade or so in fusion, are really now making visible progress to deploying machines. Some of the leading ones are literally spending billions on fusion equipment and are now actually important figures on the fusion development landscape. So the field is really making a transition from collaborative international government-funded experiments to a much more mixed landscape very quickly. And alongside all of this, developments in computing in particular and things like high-temperature superconducting magnets are really having a material effect on the field. So there's an awful lot happening and there's an awful lot of progress, but we still have a lot to achieve. The practical implementation of a fusion machine in schematic form might look something like this. Clearly, this is schematic, figurative, and it only represents one particular approach. In this case, it's a schematic of a tokamak-based approach using deuterium-tritium. You know, other fusion fuels are available, but the cross-section for deuterium-tritium is the largest, and so it's the least difficult reaction to propagate. So the schematic on the right shows what we have to do. We have to get a hot DT plasma. We have to somehow capture the energetic neutrons coming out, capture that, make heat. That might feed into a conventional steam power generation system, or indeed we might be looking to use that process heat more directly for industrial applications. Then in a DT machine, we actually have to create our own source of tritium by breeding it. So we would do that by probably surrounding the reaction with some sort of blanket. In this case, you can see we've drawn in a lithium blanket where the energetic fusion, DT fusion neutron interacts with the lithium, actually produces tritium as a byproduct of that reaction, which we can then inject back as a fuel, and deuterium is a plentiful fuel. So in principle, if we can get that breeding ratio, we can make that reaction self-sustaining. If we can generate sufficient power out of the plasma, we can generate power that will drive the turbine or be used for our process heat. So that's the concept. But the details of that, of course, the actual practical details of making that work, both as individual processes and altogether, are really quite significant. So just as an overlay over that, here are some of the current challenges that the fusion field is wrestling with. And some of these are different for different technical approaches, but some of them are in common. And I've put top of the list, what will the cost be? Because the simple answer at the moment is we don't know. Fusion is an enormously exciting source of potential low carbon power, but we actually don't know what the cost will be. Probably dominated by the capital cost of the plant, as is in conventional nuclear fission power, but we still don't know what that is. There's an important question about applications. We'll come back to that. And that has an implication for the design of the fusion machine, because some applications, say for industrial process heat, which could be very energy intensive and important to decarbonize, might use a different temperature regime than we would use for generating a conventional steam cycle. A key challenge that has been underpinning fusion for quite some time, particularly DT fusion-based systems, is how to manage the highly energetic neutrons. These are both good and bad. I've described two good uses of these energetic neutrons. They convey most of the heat from the fusion reaction, about 80% of the energy from it, to be captured as heat. They also can breed tritium. But another effect of the energetic neutrons is they have a damaging effect on the materials that you build your very expensive fusion machine out of. So clearly managing neutron-tolerant materials and shielding is a very important aspect that the fusion community is still in the midst of. All of that actually feeds in to the cost of the machine, because the lifetime of this machine, given it's a capital-intensive machine, will be very important to determining the cost. So many important aspects. I've listed some of them here, all active topics and all topics that UKAEA and organisations around the world are in the midst of. And because they're difficult and because all of this is challenging, of course, doesn't mean that we shouldn't be doing it, because ultimately the prize is very substantial. I mentioned earlier that it is not a necessity that fusion is necessarily associated with electrical generation. We normally, certainly in the fusion community, assume that that will be the case, but it doesn't have to be the case. And there are actually potentially other aspects. Perhaps arguably, fusion could be applied to areas of energy that are more difficult to decarbonize than electricity generation, such as industrial process heat. So this chart attempts to lay out some of those other applications, clearly not all equal in value, clearly some more speculative than others, but also an active topic of research about how we might be more perhaps creative in applying fusion as an energy source to some of our wider challenges. And then, of course, a key question that we're here to address is what share of the future portfolio of energy will fusion take? And of course, again, the simple answer is we don't know. Fusion is likely to be highly dependent on the cost, obviously, but also we assume that it's going to be highly dependent on geography. There are certainly areas of the world that are blessed with natural renewable energy resources more than others. There are places where energy is variable renewable energy is in abundance. In our part of Europe, we're blessed with the North Sea, which is a magnificent resource to have. But not everywhere in the world has that, and there are locations in the world that need high energy density. They have poor availability of renewables. So geography will matter, and the levelized cost of electricity will matter a great deal. The generation cost of fusion obviously will depend on the capital cost of the plant. And the focus in the fusion community is very much turning to how to make that cost effective. Not just, of course, construction costs, although that's a key part of it, but also lifetime and uptime of the output. So there are a number of really important factors that need to be built into our technology development that are becoming increasingly important as we think about deployment, that are more than just the just make it work approach to fusion as an R&D activity. So I thought I'd just finish by mentioning what is happening at UKAEA, and in the UK we have an approach to fusion for the country, and it really divides neatly into two parts as described here. The first one is actually to build a prototype, because one of the challenges of fusion is not just the individual technical solutions of those challenges I listed earlier and more, but actually also integrating them all together in a design that actually works. So we are tackling that very substantial problem. We have a program called the STEP program, which is designing to produce a prototype net power producing plant by the 2040s. And then alongside that, we are actually trying to create the industrial base that will provide the component technologies that will enable a future fusion industry of whatever shape in the future. Thank you.
Yeah, thank you very much, Tim. Before we go ahead, just a remark, because this came up in the Q&A already. We are collecting your questions, so we try as far as possible to answer all of them. We collect them, organize them a bit, and then try to feed them into the discussion after the talks, so they will not be lost here. Yeah. Okay, now we will change the topic slightly. Yeah, go from fusion to wind energy. And Claudia will introduce the topic. But well, if you allow me a remark, I think this is also a topic which shows that sort of even in things which we are used to today, R&D and basic research is still ongoing. Go, please, Claudia.
Yeah, thanks. So yeah, my name is Claudia Brunner. I'm a group leader at the Max Planck Institute for Dynamics and Self-Organization in Göttingen in Germany. And so yeah, my research group sort of looks at the fluid dynamics of wind energy. So just one aspect of wind energy as a technology, and we're really sort of at the fundamental end of the research space in this topic. So let me share my screen. Okay, is that showing correctly?
Perfect.
Okay, great. So, okay, sorry. Yeah, okay. So I want to start sort of by motivating a little bit, yeah, as was already mentioned, why we still do sort of scientific fundamental research on wind energy. Because over the last 3 decades, wind energy has transitioned from this very esoteric niche technology to one of the world's main sources of renewable energy, and is using some of the largest machines ever built. But on the path to a carbon neutral world, we are still at the beginning. So if we look at projections from the IEA, they say that a net zero global energy sector requires more than 10 times the wind energy that we have today. So there are a whole lot of challenges that we need to overcome to actually achieve that. And maybe we'll talk about some of those in the discussion. But what I want to focus on here is the fact that we don't actually understand enough of the underlying physics to leverage wind energy in an optimal way. And that there's really no way to achieve these very ambitious targets without major advances in sort of wind energy science. Because so far we've basically sort of picked the low-hanging fruit by putting wind turbines in the windiest places that we could find, and using relatively simple engineering models to predict their performance. But going forward, to achieve these goals, we need to build wind turbines in atmospheric flow conditions that are not ideal, in configurations where they affect each other, and also in numbers where they affect the atmosphere at larger scales. And so, yeah, in other words, we need to sort of understand wind farms in the atmosphere as a complex system. But I want to take a brief step back and start by asking ourselves what information we actually need from a practical standpoint to build and operate a wind farm in an optimal way. So to build the farm, you would like to know beforehand how much power it's going to produce on average and how much maintenance it's going to need over its lifetime. And so today neither of these questions can actually be answered with very much confidence. So the uncertainty in these questions is surprisingly large still. And in economic terms, uncertainty means risk, and so that means additional cost. And once the farm is built, you'd like to know, based on the weather forecast that you have, how much power your farm will produce, say tomorrow or at some point in the future, so that you can plan the electricity grid and account for the supply you will get. Because if you think about it, electricity demand has always had uncertainty associated with it. But when we were using fossil fuel, like gas and coal power plants, they could quickly respond to fluctuations in the demand. But now, as we're replacing more and more electricity production with wind and solar, not only can we not respond to the demand fluctuations, but they also introduce their own fluctuations that are difficult to predict depending on the weather. So as wind and solar become a larger and larger share of the total electricity supply in the grid, being able to accurately predict these fluctuations in the power produced become more and more crucial. And so, yeah, the question sort of is like, why is that actually so difficult to do still? So At the most basic level, a wind turbine basically sees an inflow with a given velocity, a wind speed, and then that causes the turbine to rotate. It extracts kinetic energy from the flow, converts that into electricity, and so the flow that's downstream of the wind turbine has a lower velocity. So this part we understand very well, basically. But then in the real world, of course, it's not so straightforward. So wind turbines are located in what we call the atmospheric surface layer. So that's the lowest layer of the atmosphere. And this in this layer, for example, the wind speed changes with height quite a bit, depending on the atmospheric conditions. So it's zero at the surface of the Earth, and then it increases quite rapidly through sort of the first 100 meters or so, and continues to increase until it reaches sort of geostrophic wind speeds. And so depending on the size of our turbine and the current atmospheric conditions, the wind turbine sees very different wind profiles, and that affects the power production. Also, if there's complex topography like hills or other buildings, that kind of thing, or if you have upstream turbines, that can also change the sort of the inflow that the turbine is seeing. And so you have already a very complicated flow that you have to predict how much power will result out of that. And then we also have turbulence. So the lower atmosphere is always very turbulent because this velocity gradient that I just showed leads to very strong shear, and so that inherently produces turbulence. And so this turbulence has a very profound effect on a turbine and also the flow behind the turbine. So the main challenge in this field is sort of that this turbulence spans an extremely wide range of scales. So the smaller scales here are on the order of millimeters, and then the largest are on the order of kilometers. And these scales are coupled through the transfer of turbulent kinetic energy. And so because the fluid dynamics in general, and in particular turbulence, are highly nonlinear and non-local, it's extremely difficult to make predictions. Also, our numerical simulations of these types of flows are extremely computationally expensive, so we cannot resolve all the scales that are important. And we also, in a technological application or commercial sense, you can't do these numerical simulations that are done in science to optimize your wind farm. So there's sort of inherent challenges to dealing with highly turbulent atmospheric flows with different weather conditions. And then the wind turbine itself is also a multi-scale system. And at each scale, the turbulence then interacts with the wind turbine in different ways. So for example, at the surface scale, inertial particles like rain and ice and dust, salt, impact the blade and erode it over time. And so that changes the whole flow of the blades, and it reduces the power output. And it's very hard still to predict what erosion will occur and what the result of that erosion will be. And so constant monitoring is basically needed to make sure that your wind turbine is still operating as it should. At the blade scale, these shear and turbulent eddies that I talked about lead to very highly fluctuating forces on the blades, which impact the turbine power output and also the lifespan, because you can imagine if the flow is sort of changing, oscillating quite in quite extreme ways, that causes the blades to actually oscillate themselves. So the larger your turbine is, the more flexible the blades become, just out of structural reasons. And so, yeah, there are interactions between the flow and the blades that really can lead to fatigue and damage over the lifespan of the turbine. And so it's actually quite also difficult to predict how long your turbine will actually last, because that depends on what the turbulence will be at that location. And yeah, we don't have the understanding to actually say, yeah, will your turbine last as long as what your financing was laid out to be? And then at the turbine scale, the wakes of upstream turbines negatively affect downstream turbines. That affects the power output. I'll talk about that in a second. And then also, if many turbines are grouped into a farm, then the farm itself can create a wake that is large enough to impact the atmospheric boundary layer itself. And so there it sort of raises the question, to have accurate numerical weather predictions in areas with a lot of wind turbines, how can we better understand these interactions of the turbines onto the atmosphere so that we can incorporate that into numerical weather predictions, for example. And so, yeah, I just wanted to pick out sort of one example problem that is quite sort of a central question in the field right now, to give you sort of a sense of the issues involved, which is what I had mentioned, this turbine-turbine interactions. So you can see in this photo actually that so this is the weather conditions in this photo so happen to be such that you can see the wake flow behind the turbines, and you can see that this wake extends really for kilometers. And depending on the weather, the wind direction, you're always going to have some situation where there are wind turbines located right behind other turbines. It's not something you can entirely avoid, but there's a lot of research going into understanding how can we control a farm in a way that we minimize these negative interactions by, for example, steering the wakes, or saying perhaps the first row of turbines produces less energy so that the second turbines can still produce more. So there's sort of optimizations that you, in theory, can do over the entire farm to maximize farm power output. But currently that's not done in commercial wind farms, to my knowledge at least. And so this is an active field of research where we need to understand what actually the flow looks like downstream of a turbine, so that we can, once we understand the mixing processes and what the turbulence is doing, we can develop optimizations for that. So yeah, that is sort of at the turbine scale. And then you can imagine that this farm, if it has so many wind turbines, it's producing actually a farm wake as well that can then affect other wind farms downstream. And that becomes a very interesting problem, because if you're optimizing your single farm, you have one operator who's trying to maximize energy over that farm. But if you have different farms, they can be operated by different companies, they can be in different countries. And so there's sort of another layer of how do you deal with that if, say, you built your wind farm here, but then 10 years later, someone else builds a wind farm just upstream of you, and that reduces your power output by a lot. So there's sort of these intersections between understanding the actual like fundamental fluid dynamics and physics behind these wind farms with what does that mean for technology development, but also for policy, the policy space. So yeah, I want to end here, but I hope that this could sort of give you an insight into what are the fundamental questions in the space of wind energy that we need to understand to make faster progress in wind energy production. Thank you.
Yeah, Claudia, thank you very much. And let's go immediately to our, let's say, final presentation, yeah, which is the most general one, yeah, so by Thomas, but he will introduce himself and still missing your slides, yeah.
Can you see now my slides?
Yes.
Okay, so then I'll actually start. So my name is Thomas Hamacher. I'm a professor at the Technical University of Munich and working in the field of renewable, but also nuclear energies. I'd like to share a few thoughts with you, which probably are not so purely scientifically based, but which are more, let's say, based on some observations which I recently made. And the first thing I like to address is that we are probably very close to some very drastically change in some parts of our energy system. And let's call this a solar revolution. It will not change everything. I guess that's very important. We should not, whenever we talk about also renewable energies, we know that it is not easy to just replace everything. We will replace a certain fraction only. So if we look here to this picture, this is actually the electricity prices, I think, for households in the world. And the first thing you observe is that you have very different household prices for electricity. And I show this because I think you are always quite surprised to see that we have solar energy employed in some parts of the world, like, for example, Germany, where actually there is not so much sun. While in other parts of the world, like, for example, Egypt, where you expect to have a lot of solar systems being employed, you see they aren't. And if you see into the electricity price that you have to pay in Egypt today, you see immediately why this is the case, because the electricity price is so low that it's very difficult to compete for solar here against the very highly subsidized price, which is more or less dictated by the government. So we have to see this at the first that we have very, very diverse electricity prices. Electricity prices in the world are very much dictated by regulation. Sometimes they are down subsidized. Some say they have a lot of course of taxation on top of it. But that is first thing we need to observe. Now we come to what we also, some people in the chat said, yeah, we have seen a lot of reduction in the PV costs in the coming years. Let's say, talking in some parts of the world with 800, maybe soon we see $600 or euro per kilowatt. And of course, if we take certain annuities, we see we're coming down to rather low electricity prices, which are at least on a certain basis very competitive. And of course, if we talk about a region like Egypt, we would have something like 2,000 full load hours. So we even would be able to compete with the very low electricity prices we see. But again, we are not seeing that happening these days. Why don't we see this happening? I mean, it's not only in this part. In some parts of the world, we don't see it happening because some of the governments somehow are having problems with it and try to not make feed-ins and things like that very simple. On the other side, we have, of course, a lot of customers who are just not used to it. We have electricity companies who are just not used to it. And so we see only in very few spots actually coming these electricity production by PV being employed in a very large manner. But it's very likely that this is, if we talk here about physics, it's more like an overheated liquid. And I think we will soon see that most of these countries will at least employ something like 10, 15, 20, 30% of the electricity by PV because it's just economically viable. So now we see another thing happening, and it's amazing. We don't see this probably so much happening also in Europe. We see it in Europe, but if you go to other places, I have been this year to, for example, Uruguay, and you probably don't expect that to happen in Uruguay, but if you look on the streets in Uruguay, you see a lot of electric cars, much more than you would probably expect from the first prejudice. And of course, you see most of these electric cars are, of course, Chinese electric cars. Actually, also the PV modules we saw before are mainly Chinese PV modules. So, and we will see, of course, now something new coming up. We see a new symbiosis of having PV being employed in many parts of the world. But of course, PV is a flexible supply. And now you need flexible loads. You need some loads which are able to capture the supply in the moment when it's really supplied. And that is, of course, with electric cars, if you develop a very nice charging infrastructure, which is not easily done, but it could be done, then of course you would see that you first bring in, let's say, 20, 30% of electricity, of PV electricity into the electricity system. And then you bring a lot of this electricity into the traffic system. And so without being too, let's say, over-optimistic, I think we will see in the next 5-10 years a major change in most of the energy systems in the world. Just economically driven by the fact that we will have PV, driven by the fact that we will have electric cars, cheap electric cars, both from China. So that is something which we see. But that does not mean, of course, that we have a complete change of the systems. I mean, we will not be able to supply all the electricity with PV. We will maybe be able to supply a large fraction of the traffic with electric cars. So we need to do more than this. But what we will see is that, of course, the current systems as we have it today will be mainly challenged by this. So if I have a fluctuating, rather low-cost PV electricity source, which is operating only during the days, this will, of course, challenge the classical power plants. And here there will be a conflict, which will probably first be solved by not allowing the PV. But once the PV is in the system, we will see here major changes. And now the question comes, what is next now? What will be the next steps that has to be done? Because with the PV alone, with the electric cars alone, we will not make the decarbonization step. So now a lot of options are actually I haven't mentioned all the other renewables. I think the wind energy was mentioned. That will certainly also add another addition to it. But again, it will not do it alone. We need some other elements in our system, because we have to be well aware we need to serve the mobility. We need to have heat, not space heat only, also process heat. And we also need, of course, beside the electricity, which I'm not mentioning here, we need also to supply some feedstocks, for example, for chemical industries and all of these things. So what are the options that we have here? First of all, yes, we will probably see something like carbon capture and sequestration, which actually works. If we see in our modeling results, it works very nicely together with PV. Yeah? So during the night times, at least for some parts of the world, during the night times, you have your carbon capture power plants operating, and during the daytimes, you have a lot of PV. And with this, you can make a very fast decarbonization, even in places which are still very much relying on coal power. Yeah? We might see, of course, that nuclear comes back, and nuclear will not come back in first place in the form of fusion, but in the form of maybe some Korean nuclear power plants, which, as they were built in the Arab world just recently, where we saw that they can be built in time and more or less cost compared to what happened in Europe in the last year. So this is also a possibility. And of course, then we need to have some chemical energy carriers in the system, which we are so much used to, having natural gas, having oil. So we need a replacement. Of course, everyone is talking about hydrogen these days. Whether it will be in the end hydrogen, we have to see. But we need something which is a chemical energy carrier, and which we have to develop. And of course, that needs in the first place, again, the electricity. Or if we start earlier, we can do it also with carbon capture and make some, for example, blue hydrogen, which is also an option which we should think about if we really want to make a fast decarbonization. So in the end, I think I just like to summarize. I think we are on the edge to get some new technologies into the market, mainly driven by economics. Yeah? So the economics of the PV will be overwhelming to some extent. That alone will, of course, not change the whole system. Yeah? We will get the electric cars as a major addition, which is very important. And now it depends whether, for example, heat can couple it. We just looked into the ASEAN region. If you have a PV system which can also at least produce some kind of heat, and you can store the heat quite easily, you can really make nearly a base load heat supply with PV and storage systems. It's very attractive also from the cost, if you think about it, having it in an area where you have 16, 17, 1,800 full load hours of your PV through the year. But we will see also that the other backup systems like CCS, nuclear, or whatever we can imagine we make as synthetic fuels from which source soever, we will see that there are also some backup technologies being developed. And how these systems in the end will really emerge, I don't think that we have an idea today, and we should probably also not do as if we know. But we know there will be a change, and the very good thing is this change will be driven by economics. So we probably don't need to be too much scared if there is some countries dropping out of the Paris Agreement, because this kind of pressure to go to the most economic solution will be there, and this will certainly make a change in the near future.
Yeah, thank you very much on this, let's say, very optimistic view of seeing things. Well, thank you to all the speakers. We start now the discussion, or going through the questions. To start with, I would like to take the liberty to put up a few points. Maybe the idea is to start a discussion maybe on a little bit on more general terms. And then when Karin and Georg have sort of tried to compile the questions, go into the individual points which were raised, to the certain topics, to the specific technologies, if that is all right. So where is it? So this is, I have to ask you, do you see the correct slide? Yeah. Okay, you're nodding. Thank you. So just as an idea or to maybe organize this a bit. Well, one thing is, you've seen this in the question, is also a timescale question. Yeah, so we talk a lot about net zero by 2050. I think often it's not really explained what this means in terms of energy consumption and new technology. So the question is here, is this ambitious or unlikely? This goes a little bit also in the direction of the fusion colleagues, yeah, because of course there are timescales. But this couples directly to the next point. I don't think, well, I mean, the world is not a static world and will never be a static world. Yeah, so we will also have to cope with rising demand. Then we had this as an example here very nicely. What is the role of basic research and technology development in all this? Yeah, and we will, I guess this goes along with what Thomas said, shift from fossil fuels to other raw materials. So we will have also a shift in the supply chain, a very significant shift in what becomes important. Yeah. Then this is a question, is there a correct timing for new technology? So what are opportunities? And then maybe we can also talk a bit about the concept for a future energy mix. Or, well, again, this is probably not static, but will also be a development. Yeah. So yeah, just let's take this as a teaser, as a trigger, and maybe have a discussion. Well, a few comments by the panelists, how they sort of well, think sort of the point they would make with regard to these points. I don't know if some of the fusion, Melanie, yeah, has raised her hand, so please.
Hello, yeah, a couple of thoughts on particularly on the top two. I think personally, I think that net zero by 2050 is looking very ambitious, and unfortunately, like, looking more and more unlikely the closer we get to it. I think we're making a lot of progress. Of course, a lot has been done, but to your second point there, rising energy demands. I think that the the rollout of AI has just like obliterated all progress that we made with renewables that have been put out. I think even before AI came out, the renewable capacity that had been added was not actually reducing the fossil fuels in the mix. I think it was just being taken up by increasing demand. So I think the answer to that is that, like, we need to do everything we can. It's not about which technologies should we use and which would be better. I think we need everything everywhere all at once. Of course, it comes down to money, and so it's difficult. But people talk about fusion a lot, and yes, it's ambitious and it's not going to be ready in time. But I was at a clean tech conference a couple of weeks ago, and they were having similar discussions about, like, storage to decarbonize the grid, in order to actually decarbonize enough to reach the energy targets. They need to have I think they needed to have an increase in the storage capacity, like 4 times as much as the most optimistic scenarios. So it's very, very difficult for everybody. So I think we need to be remembering that we need everything. We need to be throwing everything we can at the problem. And the other point that I would like to make is that 2050 is not the end. People often say, oh, but if fusion's not going to be ready for 2050, then, like, should we be doing it? Maybe we could spend the money better elsewhere. And yeah, of course, finite resources, it's worth thinking about. But I just think that 2050 is not the end. There are studies like charts by the International Energy Agency which show that even if we do hit the net zero targets in 2050, there will still be a big chunk of fossil fuels in the mix, probably to the tune of 20-25% fossil fuels in the mix, hopefully with carbon capture and storage. But ultimately that needs to be reduced to zero. So we're going to need something into the longer term, even if we are able to let's hope, meet net zero targets with everything we can throw at it now by 2050, we've still got a lot to do in the longer term. We'll still need sustainable energy sources. And I believe we need to be, in fact, it's not just my belief. I think the studies show that we need to actually go into negative emissions. So we need to start drawing carbon dioxide out of the atmosphere to undo some of the damage that we've already caused or that we're going to cause in the interim. And so we need more. We need a solution like fusion that can go into the long term, undoing some of the damage that we're causing. So yeah, my feeling is that it's not so much about the date itself. We need to be doing everything we can to meet the date, but we also need to acknowledge that we need a lot more energy going forward beyond 2050. And so that's why it's still worth researching these more ambitious technologies.
Yeah, thank you. Thomas, you wanted to say something, or did you?
Just I think the number, I mean, actually, I think last year it was the first time that as much PV was implemented, like to compensate the rise in the demand. So that was for the first time. But of course, I mean, we see this is just a question of setting up more manufacturing capabilities, and I mean that is also a question of time. But we are now at the edge that we produce more than the increases, which is of course not enough. But I guess here we have reached some first breaking points.
Tim?
I was just going to address the question about R&D and what we spend on it. I mean, I'm obviously a great believer in technology development as a potential solution to our challenges, but I don't think the greater we should fall into the trap of thinking that we can just R&D our way out of the current challenge we have, because we are on track to use resources. Humanity is on track to use resources at a rate that just looks profligate and unsustainable, of which energy is one, and R&D alone won't get us out of that hole. So I don't have a solution, but I do think it's not just about R&D. In the context of R&D, I think there were a few comments in the chat on the way, I think, about how we spend our money. I think I'm right in saying, and I mean to check it, that the global public expenditure on energy R&D is broadly similar to the global market for potato chips. I'm a big fan of potato chips, but to me, it feels like we could easily spend an awful lot more on energy R&D, as it's fundamental to keeping humanity alive, and still address the problem. So I don't think we should be in the business of competitive R&D spending. I think we have to look at all of it. But even that, I think, isn't enough. I think there has to be sort of behaviour changes in the whole of society, which is a really challenging thing to implement.
Yeah, Claire is next. Claudia, sorry.
Yeah, I guess just I fully agree with the previous comments made, and I guess about this time moment of 2050, like that there's nothing magical about that, and if we don't hit it, like it's not worth pursuing. Like, yeah, basically, ultimately, we need to do it as quickly as possible, and clearly wind energy is sort of one of the short-term solutions to that, and trying to get there as quickly as possible. But I think there's sort of two limiting factors that are separate in a way. One is just these practical concerns that we've talked about, like how quickly can we actually expand supply chains and industry to even if we put like infinite money into wind energy today, could we actually build wind turbines fast enough to meet that goal by 2050? I think that's very unlikely. At least in Germany, if you look at how long it takes to actually get a wind turbine built from the moment that you decide you want to build it, years go by. So it's like there's challenges, just practically speaking, that don't have anything to do with R&D itself. And then on the other hand, R&D, I think sometimes we forget that the speed of that is not something that's set in stone. It depends on how much, as we said, money we put into what types of research and in science or in industry. And so, like, in principle, it would be rational to put a lot more energy, money into it to accelerate the timescales of the development. But in the context of like, yeah, the political and sort of social frameworks, I think it's just very challenging to, like, for example, if you look at these projections and how many wind turbines we would actually need to build, and then you think about what the landscape would look like if we actually built that many wind turbines, I would be surprised if there's not resistance politically or like socially to that before we get close to the targets that we need. So I think there's sort of a bigger picture challenge that is not scientific, but yeah, as this economic case gets better, so it becomes more likely that we will achieve the targets.
Thanks for this very important point, and I think relates also a bit to some of the questions or comments in the Q&A. This is about how to drive the system. I mean, Thomas very importantly mentioned economics. There's the discussion about carbon pricing, of course, yeah, and everyone is knowing this, but let's say under the political circumstances, maybe not so likely that we reach a global agreement on this very soon. Yeah, and the other point, of course, I mean, also mentioned already in the discussion here is, of course, saving, reducing consumption, and so on. Yeah, but I think, and maybe Thomas, in the course of the discussion, can say something. He's more the expert there, but also reducing consumption is mostly to start with, if you think about house insulation or building new houses related to energy consumption again. Yeah, I mean, there is also not a simple optimum. Okay, I would think Karin and Georg, I think you are sort of prepared and set up. I don't know in which direction, maybe, I don't know if you have an idea. I would suggest maybe more from this general questions first and then come to the specific ones regarding fusion, wind energy, and so on.
Okay, well, as to the general questions, you already mentioned some of them. Perhaps some original question is whether there should not be more science communication so that more people understand the importance of decarbonization. Well, that's a question that leads a bit to another direction. And if not, you already mentioned that there was this question of how shouldn't we reduce the consumption of energy, and the opinion of the panel on the pricing of carbon. If you think this could be an economic way to fight for decarbonization. Perhaps these are the more general questions I read from the audience.
Any remarks or comments from Thomas?
I might start with a few words about the consumption. I think that's it's a classical discussion about it, but we have to face that, of course, with very high likelihood we will see probably at least 1, most likely 2, even 3 billion people in Africa in the course of this century. They are living at a rather low lifestyle today, and they, of course, all of them will like to have a higher lifestyle. So to preach now to be modest, you can preach that in Munich. Yeah, that's a very good idea, maybe. But even those who think it's a good idea usually don't follow it so precisely. And so I think we need to have a lot of more energy and a lot of more materials, and if we don't, we will have huge problems. So we should not look for solutions which are beside the technologies. Yeah, so we have to find a solution within the technologies, because all the other things like the behavioral changes, the wishes of behavioral changes, are very easily converted into political suppression and whatever, and I think are very dangerous. If people want to, they should. I mean, everyone is welcome to live very modestly, but I don't think it is an easy thing to bring that onto a society. And since, let's say, most of the societies which will grow in future are very modest today in their lifestyle, we should certainly not ask that from them. So I would imagine we have to prepare for a huge increase in energy consumption in the future, and that can only be done with a lot of technologies.
Tim.
I think I agree with the premise that we, the technical community involved in energy, should do more to communicate about the challenges. I mean, one of the things I observe is the more you get into any energy, the more you realize just what a difficult, fraught topic it is. It's always easy to look at some other source and say, yeah, let's have X because that's easy. Why don't we all have more hydropower? Or let's just invent fusion and use that, or whatever your favorite one is. And then the more you know about it, the more you realize just how difficult it is. And I think that is sort of lost on most people who think that actually solving energy is a relatively easy task. Actually, as we've been discussing, it's a huge challenge. And I think it's beholden on us to help communicate that challenge, just to engage people with the scale of the societal challenge that decarbonisation is.
Claudia?
Yeah, I agree that sort of, yeah, the communication is a very challenging topic, especially for technologies like wind energy have like a lot of what I guess would be called fake information against them, and a lot of communication from other spaces. And so quickly when I'm doing these sort of community engagement events, there's sort of misinformation that is very difficult to, like, in a short way or moment to articulate the issues. For example, there's a lot of concern about, one thing in Germany that is like, what is the effect of wind turbines on birds, which definitely is a concern, but what is the effect of climate change on birds, and like how that this isn't really a question of then it's also like quickly, okay, we just need to use less energy, this thing, like we just need to choose the right one. And then there's always like the bigger picture of like what the impacts of climate change will be globally is sort of forgotten against these nuggets that have been very like popularized as issues against specific technologies, or like not unfair comparisons between, say, coal power plants or nuclear power plants and wind energy. Like that, it is very difficult in my experience to sort of, I think we need a lot more science communication, but I would say I don't have the right answer to how to do that, because often the problem is that the people who are interested know, like, are informing themselves, but how do you reach the people who are not getting that information and are being targeted by other information that has other interests in mind? So basically my point is I don't have the solution to science communication, but I think it's going to be so important. It is already so important, because a lot of the challenges that we have in the space are ultimately like political and social, and we have to live with what is politically realistic to do and not what is scientifically or economically the ideal solution.
Oh, Karin, we have changing topics, maybe shifting a little bit.
We had questions that are a bit in combination with storage of energy. Would this be an option to benefit? Would this be a benefit to wind energy to combine it with big energy storage capacities? And another one. One participant wonders that there are large-scale battery energy storage that has been implemented using lithium-based batteries, which were developed because they have a high energy density, so they were developed for cars and perhaps even airplanes. Why wouldn't you use in these energy storage farms other forms of storage? And then one proposition is that concentrating solar power plants together with molten salt heat storage, they produce a lot of electricity, 24 hours, 7 days. And it seems they are very much constructed in China, and they were not mentioned here, and they're not common in Europe. Why not? So these three questions are a bit around the topic of combining energy sources with energy storage systems.
Thomas, I think this is your terrain.
I guess the most important is first to see we should not, I mean, we have this tendency to think of one PV panel or one wind turbine and one battery beside it. And we should think of a system that we develop. Yeah? And for example, in Europe, we have, first of all, a very large European electricity system, which is the first thing we need to enlarge, so that we have some, at least wind energy is somehow smoothing if you go to bigger areas, at least to a certain extent. And to some extent is also true for PV. On the other side, we need first to think now about the coupling. Electricity is becoming the most important, as we would like to say, the most important primary energy source. It's not a primary energy source, but we can think of it like this. And so we have to bring it into the traffic sector. We have to bring it into the process heat, in the space heat sector. And all this already offers us a lot of flexibility, because storing heat is so much simpler than storing electricity. So we haven't done a lot in this respect yet. So these are the things, the first task we have. We have to make a coupling of the systems, and we have to really take full advantage of the flexibilities the other part of the system offers. Here we have a long way to go. And then, of course, yes, we have to see there are some things which, if we talk about intermittent renewable energies, we have on one side day-night, or in wind we have weekly changes, which might be able to store like with these systems. But then we have also some seasonal variations, which are more long-term variations, which can only be probably kept with some chemical storage systems like hydrogen or others. So that is something I guess we certainly need to work. And the question about the batteries, yes, of course, we can think about stationary batteries in slightly different systems. There is a lot of, let's say, research in this direction using other chemistry or redox flow batteries. Here, I think the race is open. Beside the solar thermal, I guess solar thermal is actually, we have in Europe a few solar thermal plants. Just go to Seville in Spain and then you can see them. So they do exist, but of course they have, compared to PV, just economic problems. Yeah? So the economics of a solar thermal power plant is, by today, is so much worse than a PV panel, and it is not, let's say, the advantages of having storage is not not compensating for the disadvantages in the prices yet. That might change in the future, but we have a lot of, or we had at least in the past, a lot of development of solar thermal in Europe.
Tim?
If I may, I was going to ask a question as a follow-up, if that's all right.
Yeah, you're welcome.
So renewables, variable renewables are great. But they have a sort of a habit of being in the wrong place and the wrong time for the consumption. So my question was, what do we need in order to be able to make efficient use of the variable renewables, wind and solar, to address both the temporal and the spatial inconsistency with the consumption?
I mean, we certainly need to have power grids. I mean, that's the first thing. We need to have a power grid. That is something which is, I think, it came out of most of the studies since 20 years. Unfortunately, I mean, we have the same problem with building power grids that we have with building wind turbines. Although power grids are loved by birds, actually, the birds like to sit on power grid, but the people don't like them somehow. So I think that is the first problem. Yeah, so it's we were unable to build the north-south line in time. For example, in Germany, it would be very beneficial to integrate a lot of the wind energy, which is produced, for example, in the northeast of Germany, where it's not so much consumption. So that is an issue. Yeah, and it's tricky. I mean, it has nothing to do with technology. It has nothing to do, I think, with major environmental impacts. It has only to do with a lot of prejudices against these technologies and people not liking the power line in their back. the temporal things I said, we have to work certainly on this integration first, of the integration of the different sectors. This will give a lot of opportunity here. Yeah, so this will give us a lot of opportunities. But then, of course, at some point, we need something like a chemical storage if we want to go only on renewable energies. Then we need something like hydrogen or other synthetic fuels. But then once we would have them in the system, I mean, we have made a lot of investigations in this direction, we get actually quite smooth systems. Yeah? And given at least the European context, we would have a lot of opportunities to store hydrogen in a very large manner, so that there is no, let's say, technical obstacle. We could discuss about the economics, but there is no technical obstacle saying, no, this can't be done. Yes, I think it can be done. It is just not easy to convince everyone to accept the wind turbines and the power grid beside their house.
Maybe since we are sort of making also time is progressing, there were a couple of specific questions to the different technologies, and yeah, so both to fusion, maybe to start with, I don't know, it's somewhat higher up, and then I remember one regarding also the wind energy question, yeah.
Yeah. Okay, and fusion, there were some specific questions. One is the question of flexibility of fusion energy generation, and no, of course, estimated time needed until the first continuously running fusion system could work. It's, of course, difficult to answer, but could it be used also locally? Question of flexibility.
I think this was related to the minimum size of a fusion power plant.
Yes, yes.
I'll have a go, and Melanie can then have a better go. Actually, Robert, you could have a good go at this as well.
Yeah, I could, but I'm here, the moderators.
I mean, certainly from in tokamak design, fusion systems have quite large recirculating powers. So generally speaking, they look more economic at larger size installations. If that logic follows, then they will be more suitable to conventional large-scale energy plant like gigawatt-scale generation rather than local generation. Is it possible that some fusion technologies could be used at a much smaller scale for local generation? Yes, it's possible, but at the moment that's a less mature line of development. And I think the other question was about load following. No, in principle, most fusion technologies could be used for load following. But on the other hand, probably one of the inevitable attributes of them is that they're quite high capital cost machines. If that is the case, then the economics will probably dictate that they're basically used as base load, so run flat out all the time, which is the case with conventional nuclear as well, which is capital intensive. So at the moment, it looks like more base load run continuously and not local, but things could change.
And can I just add to that? I agree completely. But there have been some studies or people starting to look at the possibility of cogeneration, like for exactly that reason as well, because of the high capital costs of fusion power plants. You'll want to keep them operating as much as possible. And so if there is a lot of variability in the grid because of renewables already on the grid, then this actually could become more of a problem, and so there could be a necessity to co-generate. So maybe switch from producing electricity to maybe producing heat, or you could maybe thermal storage. People are investigating different things, so that could definitely be an option. And on the scales point, yes, there are different designs. There are different private companies are investigating different concepts, and so there are some the physics is further behind the larger scale ones like the tokamaks and the laser systems. But if the smaller ones could be made to work, as Tim mentioned earlier, they could actually have a different part of the market. So there is a possibility, if some of these different concepts work, that there could be smaller machines, maybe more local ones, maybe like hospital generation or things like that, alongside the bigger baseload machines. But this is something that we just don't know yet, because it depends what works and what doesn't. But I do know that there are private companies who feel that they're not in competition with each other on different scales, some aiming for like 100 megawatts, others aiming for gigawatts, for example.
Yeah, so thank you. Yeah, Thomas wanted to respond to that as well.
Yeah, so we have made some study about the variability of the fusion, and as first thing, yes, you can build even, let's say, with some heat storages in the fusion system, you can have a system which really works also in a renewable future. So that is something we should, and here we should need to understand one thing. Renewable systems have a negative economy of scale. So if you want to go with a system from 60% renewables to 80%, it's more costly than to go from 40 to 60, and it will be even more costly to go from 80 to 100%. So at some point, it is extremely valuable to have dispatchable power, yeah? And that can be filled by many very high cost technologies, and fusion could be one of those. So we should never forget that. It could also be conventional fission, of course, could be CCS plants. We should be very, very, just making the comparison of the low PV cost now with the fusion cost is completely misleading. If you talk about the first 30%, it's true, but if you want to talk about a big system, it's no longer true. Therefore, yes, don't be scared by the high costs. If they can cover the last 20%, we will be very happy. We will be very happy. Yeah? So, and the second thing is when we talk about the size. I mean, I don't know what people want with small power plants. I mean, we are talking about many cities in this world, in Africa and Asia, which have tens of millions of people. You think you can supply them with a small power? No, you want to have huge power plants, and therefore it's a complete wrong question. I think it's people who always ask this question haven't gotten the problem. We will see so big cities, especially in Africa, coming up, which will require so much energy, and we will be happy if we have large-scale fusion power plants to supply it.
If I don't want to take your part, Karin and Georg, but I remember now, maybe for the last minutes also, giving Claudia opportunity, there was a very specific question about the lifetime of the blades. I mean, you mentioned this, and I think this is something.
Yeah, there were two questions about the blades and about how the wakes of the farms, how long they last. So regarding the blades, it is a really big problem that has sort of more recently caught attention, because you have to think like the difference between like an aircraft and a wind turbine is you can't just go and check if the blades are still doing okay, because that in itself is costly. So it's sort of two problems. How do you even tell whether your wind turbine is still okay and is still the blades have not eroded and it's still working as it should? And then if you know it's bad, what do you do about it? But you can change sort of the surfaces of the blades without having to change the entire wind turbine blade. But these are things that are expensive, and this goes into this operation and maintenance cost that is a significant chunk of the cost of wind energy. So even knowing, like being able to predict it so that you don't have to go out and fly a drone in front of your wind turbine or this kind of stuff, that already would reduce the cost of wind energy a little bit. So it's all these small little things that add up to create the cost of wind energy in the grid that we have today. And then the other thing was regarding how far the wakes can exist downstream. That's sort of exactly what is very hard to predict and what we're trying to understand scientifically. One problem is also that information on, say, the power production of turbines or farms is not publicly available. And the companies, like for good reasons, they're very concerned about the competitors finding out how good their turbines are and where the good locations are. So they, it's very hard for us as scientists to actually get access to enough data to be able to make predictions or understand these phenomena given the wind farms that we have today. And of course, it's not something you can simply like recreate on a with scientific scales. So that's part of the issue. Studies have found that you can see the effects like 50 kilometers downstream. So these are really big interactions with the atmosphere that have major effects. And in places like the North Sea, where we're building a lot of wind farms close together, it's definitely important. But that's sort of exactly at the heart of what we're trying to study in the scientific sphere.
Yeah, thank you. Is there we are coming very close to the end. Is there anything on your list, Karin and Georg, which you think is maybe as a final remark, wrap up round?
I think the most things were discussed. We had questions on fusion, we had questions on wind, on solar, on storage, on the grid. So I think there could be a lot of other points to be discussed, but it's not possible in such short time.
Yeah, I think then it's time to come to a close. I think we had it was a very interesting discussion. We had a lot of insights into very different technologies and energy questions. Regarding the many questions and comments, so please apologize if we couldn't answer all the questions, but I think we tried to at least cover more or less the main points and concerns. I hope you enjoyed the presentation and the discussions. Yeah, so I think it's also time to thank IOP and German Physical Society for organizing this. Yeah, and the organizers who made this possible. Very special thanks to the panelists, who were prepared to participate here in these meetings. And then finally also thanks for joining this meeting, from wherever you are and from wherever you come from. As a final point, there is a follow-up, not on energy, so you have to ask if you have final questions to a different audience or use a different opportunity, but apparently, well, not apparently, next year there is the quantum year, so there will be a meeting in a similar format on quantum physics next year, and well, different topic, different opportunities, and so final big thank you to everyone, and